we are going to derive the molecular orbitals for a tetrahedral compound or a tetrahedral complex by using the Kim method developed by Shun K. Kim of Temple University. Professor Kim himself called this the Correspondence Theorem. The first step is for us to derive coordinates for the 4 equivalent atoms on which we're going to put the group orbitals. We imagine that the central atom or metal is going to be at the center, which would be the origin in this particular coordinate system. To the right is the positive x direction. To the back is the positive y direction. And coming up is the positive z direction. We label the sigma orbitals found on each particular atom as S1, S2, S3, and S4. And we put the appropriate coordinates in front of each atom or orbital. So this particular atom is placed, goes 1 unit to the right, 1 unit to the back, and 1 unit up from the origin. Therefore it has the coordinates 1, 1, 1. For the second atom, we go to the left, so that's the minus x direction. We're coming towards us, so that's the minus y direction. But we're going up, so that's the positive z direction. Therefore the coordinates are -1, -1, +1 for orbital S2. For S3, we go 1 unit to the right, so that's the positive x direction. We're going to the front, so that is the negative y direction, so that gives the -y. And we're going down 1 unit, so that is the minus z direction for orbital S3. For our final orbital, S4, we notice that we go 1 unit to the left, so that's the minus x direction. We go to the back, so that is the positive y direction. And we're essentially going down from the central point here, so that is the negative z direction. So that gives us the coordinates -1, +1, -1. To help keep track that you haven't inadvertently mislabeled one of the points, we notice something about the number of negative coordinates that we have here. So in this particular case, we have 0 negative coordinates. Here we have 2 negative coordinates. Here we have 2 negatives. And here we have 2 negatives. In all 4 cases, we have an even number of negative coordinates. That will always be true. Either will have, depending upon how you set up your coordinate system, either all the coordinates will have an even number of negatives or an odd number of negatives. But if they have a mixture of each, you might want to double check to see that you may not have inadvertently miscalculated the coordinates. As a key to this method, the exact coordinates are not important. The important thing is their relative values. We have selected it as a, not exactly a unicube, because the length of an edge here is actually of length 2, but it makes for convenient coordinate sets. The important thing is that the center of all these symmetry elements will be the origin, 0, 0, 0, and that all 4 of these points are symmetrically equivalent, which means that there is at least one symmetry operation which will take one of the orbitals into the other. A single rad is like a non-degenerate representation, like our A1 or A1G totally symmetric representation. For the A1 group combination, we are able to derive it as being S1 plus S2 plus S3 plus S4. Since all of the orbitals have a positive coefficient, they're all same sign, that tells us that they all have the same phase. And they're denoted as being the same phase as all being shaded blue. The 1/2 in front here is the normalization constant, which you might or might not study in inorganic chemistry, but you will derive in PChem 2, for example. The appropriate orbital on the central atom that has the right symmetry to interact with this group combination is going to be an s orbital. Probably going to be a 2s orbital in the case of carbon if you are deriving the orbitals of methane, or it could also be a 3s orbital for a transition metal, for example. In general, s orbitals tend to have A1 symmetry. They tend to have the same symmetry as the totally symmetric representation, which is also sometimes called the identity representation. Now we would like to derive the T2 molecular orbitals, either for methane, which is a tetrahedral molecule, or for a tetrahedral transition metal complex. So to do that, we notice that for the T2 irreducible representation, we have the following basis functions, x, y, and z. They're enclosed in parentheses and separated by commas, which reminds us that we have degenerate representations. They're triply degenerate because we have a t. So you can think of that as being the abbreviation for triple or triplet. For the first member of the degenerate pair, we use the x basis function. So for that, we look at the x coordinate of each of the orbitals, and we use that value as the coefficient. So for example, for S1, we see that the x value is a positive 1. Therefore, the coefficient of S1 in the molecular orbital is going to be a positive 1. Similarly, for S2, we see that the x coordinate is minus 1. So therefore, the coefficient of S2 is going to be a minus 1 in the molecular orbital. For S3, the x coordinate is again a positive 1. So we have a positive 1 as the coefficient for S3. And for S4, the x coefficient is minus 1. So the coordinate is minus 1. So the coefficient is minus 1 for S4. So that gives us an overall molecular orbital of 1/2 S1 minus S2 plus S3 minus S4. Wherever we have a positive coefficient, that is one particular phase, which is denoted as blue in this particular diagram. Wherever we have a minus 1, that is the alternate phase, so that is denoted with a red shading in this diagram. The atomic orbital on the central atom that has the proper symmetry to combine with these group orbitals is going to be a 2px orbital in the case of methane. If we're talking about a transition metal complex from the first row, this is going to be a 4px orbital on the central metal atom. For the second member of the T2 molecular orbitals, we're going to use the y basis function. So in this case, using the correspondence theorem, the coefficient of the molecular orbital, of the atomic orbital, in the overall MO, we are going to get simply by putting the coordinate into the basis function. Since our basis function here is y, all we have to do is write down the y coordinate as the coefficient. So for example, for S1, the y coordinate is a 1, so therefore the coefficient is a plus 1. That's why we have plus S1. For S2, the y coordinate is a minus 1, therefore the coefficient is going to be a minus 1 for S2. For S3, we see that the y coordinate is a minus 1, therefore the coefficient is a minus 1. So that's why we get minus S3. And then for S4, the coordinate is a plus 1, therefore the coefficient is a plus 1. So we get S1 minus S2 minus S3 plus S4. So we've denoted the positive phases by blue and the negative phases by red. The atomic orbital on the central atom that has the proper symmetry to interact with this linear combination of atomic orbitals is a py orbital. If we're talking about the molecule methane, this is going to be a carbon 2py orbital. If we are talking about a transition metal complex, for the first transition row, this is going to be a 4py orbital. one thing to notice here also is that we go from having positive phase to negative phase. So since the molecular orbitals are continuous functions, not only continuous, but they have to be differentiable and doubly differentiable. Since it's continuous at least, if we go from positive phase to negative phase, at some point we must pass through zero. So positions where we pass through zero in the molecular orbital are called nodes. And this particular orbital has a single node. It has one node. In fact, we'll see that all the T2 orbitals have exactly one node. Whenever we have degeneracy, not only do the orbitals have exactly the same energy, but they have to have exactly the same number of nodes. For the third and final member of the T2 molecular orbital combination, we use the Z basis function. The coefficient for the atomic orbital is going to be the Z coordinate that we have from the point that we previously defined. So in this case, the Z coordinate for S1 is a positive 1, so the coefficient is going to be a plus 1, so we get plus S1. For S2, the Z coordinate is a plus 1, therefore the coefficient is a plus 1. For S3, the Z coordinate is a minus 1, therefore the coefficient is a minus 1, so that's why we get minus S3. And similarly for S4, the Z coordinate is a minus 1, therefore the coefficient is a minus 1. So we get minus S4. So one of the beauties we see about the Kim method using the correspondence theorem is that once we've defined the points, we can write down the molecular orbitals almost instantaneously. So the last combination for T2 is going to be 1/2. That's our normalization constant. S1 plus S2 minus S3 minus S4. So we've done all the positive coefficients, the positive phase as blue, and the negative coefficients as the negative phase as red. The atomic orbital on the central atom that has the proper symmetry to interact with these group orbitals is going to be a pz orbital. If we're talking about methane, this is going to be a carbon 2pz orbital. If we're talking about a transition metal complex from the first transition row, this is going to be a 4pz orbital. Again, going from here to there, we go from a positive phase to a negative phase. Since the molecular orbitals are continuous functions, if we go from positive phase to negative phase, we have to go through zero at some point. That's our intermediate value theorem that you learned in calculus. So since it passes through zero, we have a node. So we have exactly one, and we can visualize the node as kind of crossing across the waist of our cube here, and that's where the node is going to be. Again, it has one node for this molecular orbital. One way that we can assess the accuracy of the derivations that we've done using groups theory and the molecular orbitals theory is to compare those predictions with the predictions of hybrid orbital theory. So for example, if we look at water and we derive the MOs, which we haven't done so far, we get 4 different levels. So we say they're all non-degenerate. If we compare it to the hybrid orbital theory, remember that we have 2 hydrogen-oxygen bonds that are sp3 hybrids. That should be sp3. sp3. And there are 2 sp3 hybrids that have lone pairs. So we should have 2 different energies in water if the hybrid orbital theory were correct. It turns out if we used a technique called X-ray photoelectron spectroscopy, the predictions of that experimental method entirely agree with MO theory and completely disagree with the hybrid orbital theory. We find that there are exactly 4 different energy levels by using this experimental technique. The next molecule for which we can compare the predictions of molecular orbital theory and hybrid orbital theory is ammonia. We would find that if we examined the orbitals of ammonia, that we would have a ground state that was non-degenerate. We'd have a doubly degenerate pair here, and then the lone pair would be in a non-degenerate higher energy orbital. So we would have 3 different energy levels, the middle one of which was doubly degenerate. On the other hand, if we were to use hybrid orbital theory, we would have 3 of the nitrogen-hydrogen bonds would be sp3 hybrids, which would have identical energies, and the 4th sp3 hybrid would contain the lone pair, so it would be slightly hotter in energy. It turns out that if we look at X-ray photoelectron spectroscopy of ammonia, the experimental data is entirely consistent with the MO theory prediction and completely different than the prediction from hybrid orbital theory. Last but not least, we can look at methane. Now, methane is our prototypical organic molecule, and it was exactly to explain the bonding in molecules like methane that the hybrid orbital theory was invented in the first place. So let's see how well it does. We know that from MO theory that we have a non-degenerate ground state that's A1, and then we have a triply degenerate T2 state. So we have 2 different energies. The higher energy has 3 times as many electrons as the ground state. On the other hand, hybrid orbital theory tells us that all 4 of the carbon-hydrogen bonds are identical in every way, and they have identical energies. So we predict that we'd have only one possible energy, and all the electrons, all the valence electrons, would be in that particular state. Again, the experimental data from X-ray photoelectron spectroscopy are entirely consistent with MO theory and completely different from what we get from hybrid orbital theory. In other words, molecular orbital theory is always right, and hybrid orbital theory is always wrong, at least in the cases for which we compare it with X-ray photoelectron spectroscopy. Here are models of the 4 molecular orbitals of methane that we just derived. In the front, we have a model of the A1 state, and we can see that all 4 of the group orbitals on the outside are a blue color, showing that they all have exactly the same phase, and that the atomic orbital on the central atom that has the proper symmetry to interact with it is an s orbital. So, and since they all have the same phase, it's going to be a A1 bonding orbital. In the back row, we have the 3 T2 combinations. Going from left to right, we have the X, Y, and Z basis functions. So for this particular model, we see the px orbital and the proper group combinations. We can also break the model open to show the mirror plane. It gives us the same orientation that we used in the diagram. In the center, we have the py combinations. That's the y basis function. And we can see the p orbital in the center on the carbon atom, for example, that has the proper symmetry to interact with the group orbitals. And this model also has a mirror plane, so it breaks open. And last but not least, on the right we have the pz combination, the z basis function. So we can see the pz orbital in the center that has the proper symmetry to interact with the group orbitals. So we have the A1 in front, and then we have the 3 triply degenerate T2s in the back. When we have a transition metal complex, this tetrahedral, even though the p orbitals on the central atom have the correct symmetry to interact with the group orbitals, in general they're usually too high in energy. It's actually the metal d orbitals that actually have the right symmetry and the right energy to strongly interact with the group orbitals for typical ligands. So we've demonstrated that here. We've made models to show the 3 T2 combinations that'll be most important for a transition metal complex. So we can see here, we can actually see a d orbital. We can see the 2 nodes in the atomic orbital, which shows us that we have a Gerada d orbital. And since this is the x basis function, the d orbital that has the proper symmetry is going to be the dyz orbital. In the center, we have the y basis function. So we see a d orbital there. And the d orbital that has the proper symmetry to interact with the y basis function is going to be the dxz orbital. Last but not least, on the right, the D combination has the right symmetry to interact with the z basis function is going to be the dxy orbital. So the easy way to keep track of this is the d orbital that doesn't include the basis function is the one you want. So for the x basis function, we want dyz. For the y basis function, we want dxz. And for the z basis function, we want the dxy.